Hello everyone, my name is Inchem and this is my submission for Lab 3 of the CS7GV3 real-time rendering course. If we look at the screen right now, we have a cube container and a lemon. From the silhouette alone, we can tell what they're supposed to be, but visually they look very flat. The surfaces are smooth, there's no micro detail, and they don't interact with light in a realistic way. Now, if I start to increase the normal mapping intensity, we start to see small bumps, dents, and texture variations. And suddenly the lemon looks more porous and our cube looks more detailed. So, what exactly is happening here? This is the normal map that's used for the lemon and the cube. A normal map is a texture that stores surface normal directions encoded as RGB color values. Instead of adding more geometry to the mesh, we modify the direction the surface appears to face at each pixel, so it's less computationally expensive. You'll notice the distinct blue-purple appearance of each of them, and that's because blue represents a surface pointing straight outward, which is the default unperturbed normal, while red and green encode horizontal deviations in tangent space. So the RGB channels are not colors in the artistic sense, they're directional vectors. In our UI, we have a slider that changes the normal map intensity. At intensity 0, we ignore the normal map entirely and the surface is flat. At intensity 1, that's when we start to see the normals exactly altered in the texture, but as it increases past 1, the bumps become more amplified and exaggerated or unrealistic. So this value simply scales how much we trust the normal map data. To make normal mapping work, we need more vertex data than usual. Each vertex stores a position, a normal, tangent, bitangent, and UV coordinates. The tangent and bitangents are essential because normal maps are defined in tangent space. To transform these normals into world space, we construct the TBN matrix. Then, in our fragment shader, we sample the normal map and use the TBN matrix to transform into world space. That transformed normal then replaces the interpolated vertex normal in the lighting calculation. I also used a Cook-Terrence lighting model to help with enhancing the illusion of depth in the normal map. Looking back at our models, in our scene, we've shown the cube and lemon model, and now we'll focus on the rock and bench model to the end. Now, looking at our models, the large rock model has some sculpted bumps, and we can see finer surface detail once mapping is turned on. Why this is happening is because although the model could add bumps in without the normal maps, it's computationally expensive. But with normal mapping turned on, the finer details like pitting, erosion, and micro variations can be added in a more inexpensive way. Looking at the bench model, we can also see without normal mapping, it looks more smooth and cartoonish, even though the wood grain seems painted on. But with normal mapping, it looks more carved rather than printed, making it more photorealistic. And that concludes my implementation explanation of normal mapping in OpenGL and GLSL. Thank you for watching.